Hello everybody, and welcome back to more Pre-Calc 11. We are going to start a new unit today. We're going to start a unit on trigonometry, and I'm sure you remember trigonometry, your SOHCAHTOA days, and your Pythagorean theorem, and we're gonna build on that a fair bit in a way that's going to allow us to explore it future years. So we're going to talk about angles a lot today, and we're going to first talk about something called angles in standard position. So an angle is in standard position in the vertex is located at the origin, which is 0, 0, and the initial arm is located along the positive x-axis, and then the terminal arm lies in any quadrant you like. So if we think of this example over here, if I have as my origin 0, 0, if my initial arm is this one right here, so there's my initial arm, and we want to think of it as being like a starting point. So if you start at that point and you rotate to some other angle, maybe it's here, so you rotate to that other angle, then this angle right here, which I'll call theta, is in standard position. So the initial arm being start here on the x-axis, the terminal arm being rotate until you get to that certain point there in this first quadrant, as it turns out. Now, each part of our xy plane is divided into quadrants. So there are four quadrants that we're going to talk about. And so I want you to recognize that as we move around these quadrants, we're going to have different angles. So for example, starting here, this would be an angle of 0 degrees. But if I was to rotate all the way to that positive y-axis, I would have turned 90 degrees. And then if I rotate around to the x-axis here, that would be 180 degrees. And then if I keep on rotating to the negative y-axis, I would be 270 degrees. And as I continue to rotate around, I'd make a full 360. Now, of course, you could keep doing this. You could rotate again and get 450 and so on and so forth. But we're going to just talk about one rotation for now. So a quadrantal angle is any angle that lies along the x or y axes. Okay, so 90, 180, 270, and 360 will be our quadrantal angles for now. So we're going to draw the following angles in standard position. And now, as we do this, so for example, drawing the angle theta equal to 48 degrees, approximately what would that look like? We want to point out here, so if I start here, this is my 0 degrees, and if I know that this is 90 degrees, then 48 degrees would be like somewhere in between here. So there is theta, approximately 48 degrees. Go ahead and try the other ones. Just hit pause real quick and try these other angles, and then you can unpause me and see how you did. Okay, so if this is 130 degrees, if there's 0 degrees and that's 90, and over here is 180 degrees, well then I know that I'm past the 90, but I'm not to the 180, so I'm going to do it somewhere approximately over here. And that's going to be, my angle theta would be this whole thing from there to there. Okay, 229 degrees, well again, this is 0, 90, 180, and 270. So 229 is going to be past 180, not to 270, so maybe somewhere over here. I'll draw that as 229 degrees. And then last but not least, 0, 90, 180, and 270. So 300 degrees would be all the way around to about here. So this angle here would represent 300 degrees. Now, I should go back and point something out which I skipped over before, which is each of these sections of my xy plane can be divided into quadrants. And so these quadrants have numbers associated with them. So this is my normal xy plane. This region right here, this is our first quadrant. Okay, that's quadrant number 1. And then as we rotate, we think of the positive direction as rotating this way. So as we rotate around, then this becomes quadrant 2, and then this becomes quadrant 3, and then over here to quadrant 4. So if I was to say, hey, find an angle in quadrant 3, you know that I'm looking here in the negative y, negative x region of that space, okay? So with that in mind, we're now going to go back and we're going to talk about something called reference angles. So a reference angle is an angle, the angle between the terminal arm and the x-axis. Okay, so the angle between the terminal arm and the x-axis. And now we're going to go back and we're going to find the reference angles for these previous examples we just did. Well, let's go back here. Let's take a look at this one. So this was 48 degrees, right? There was my 48-degree angle right there. Well, the reference angle for this angle would be the angle between the terminal arm and the x-axis. So it would be that angle right there. And if you're looking at that and saying, Mr. Trask, that's 48 degrees, congratulations, you are right. The reference is 48 degrees. And that's kind of a feature of being in the first quadrant. So when you're in the first quadrant, the angle is the same as its reference angle. Okay, so let's try the next one here. So we know that this, this original angle here, this was 130 degrees from my starting point. But I want to find the reference angle, which is the angle between the x-axis and the terminal arm. So I'm looking for this angle right here. So my reference angle in that case is not just going to be equal to 130. But I noticed that this all the way around to here would be 180 degrees. And I went 130 degrees. So the difference there would give me that angle theta. So that would be 180 minus 130, which means my reference angle would be 50 degrees. And then let's take a look over here. This 229 degrees. If I start here and go all the way around, that's a 229 degree turn. But I want the reference angle, which is going to be between, it's going to be between the x-axis and the terminal arm. And so if the distance from the initial position all the way to here is 180 degrees, then I guess the difference between 229 and 180 will be my reference. So my reference would just be 229 minus 180, which is going to be 49 degrees. Okay, and then last but not least, let's take a look here. And so I know that this rotation came around to 300 degrees. If I kept going all the way around, it would be 360 degrees. So to find that angle right there, my reference, it's just going to be the difference. So my reference is going to be equal to 360 minus 300. And we'll see that that's 60 degrees for my reference angle. Okay, so why does this matter? Why is the reference angle useful? Well, we'll get into it more a little bit later, but I'll just kind of, I want to show you why we want to find these things. So let's imagine, for example, let's go back to the trig you know and talk about taking the sine. Okay, so I'm going to take the sine of this angle here, 130 degrees. So the sine of 130 degrees equals 0.766 blah, 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 blah. Okay, neat. What happens if I take the sine of that reference angle? So my reference angle was 50 degrees. So the sine of 50 degrees is, well, it turns out it's the exact same thing. And because of that, it's going to be really useful to know what the reference angle is whenever we're dealing with angles in general. Now, I will point out that this is not always the case. Like, for example, what happens if we take the cosine of 130 degrees? The cosine of 130 degrees is negative 0.642 blah, 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 blah. And the cosine of the reference angle of 50 degrees is positive 0.6427 blah, blah, blah. So the same number, but positive and negative. And we'll get into that more later. But it's important for you to understand that finding the reference angle is going to be like a shortcut in a lot of ways to helping us figure out what we want to know. Okay, let's take a look at this question here. So find all angles in standard position from 0 to 360 that have a reference angle of 35. So if I just remind myself, that's 0, that's 90, 180, 270, and then that's also 360. Whenever we talk about angles, we actually have to specify a range of angles, because you could go round and around and around. You could go round and around forever. But we're just going to do it for one complete rotation. Okay, so, and we're going to look for angles that have a reference angle of 35. So my first angle would be this one right here that I'll sketch out. So that's going to be 35 degrees. The next reference angle, I'm going to have to go around here, or sorry, the next angle that has the same reference angle, I'm going to go rotate around to a point where, when I stop there, this is 35 degrees. So my angle is not 35, but the reference angle there is 35. And so you could figure out that this angle here would be equal to 180 minus 35, which would be 145. So this angle right here is a 145 degree angle. I'm going to keep on going. I'm going to keep on going into the next quadrant. So I'm going to rotate all the way around until I get to this point right here, where my arm is now, again, 35 degrees from the x-axis. So what is that angle all the way around? Well, I can see that that angle will be 180 plus 35. So that would be 215 degrees. So this angle here is 215. And then I'm going to do one more where I keep going around, and now I end up in the fourth quadrant, where I make a 35 degree angle between the x-axis and the terminal arm, which means I go all the way around, keep going around to here. And that angle there, you could see, well, that would be 360 degrees minus 35, which would be 325 degrees. And so this angle here is 325. And so the angles 35, 145, 215, 325 all have the same reference angle, which is 35 degrees. Okay, last thing we're going to just kind of throw at you here is we're going to talk about these special triangles. Aren't you lucky? You get special triangles. So there's two kinds of relations, two kinds of triangles that we're going to look at, where you're not going to need to use your calculator to find the sine, cosine, and tan functions. You'll remember that good old TOA tells you how to find the function for how to find the ratio for any given angle. Now the two kinds of triangles, we're going to get into this more later, but basically if I have a right angle triangle, I can use my SOHCAHTOA. The first special triangle is one that has a 30 degree angle here and a 60 degree angle in the other corner. And it doesn't matter where they line up, because we know that all these angles have to add up to 180. So if I have a right angle triangle and one of the angles is 30, the other angle is automatically 60. Well, it turns out that these have a very special relationship, where the shortest side of this triangle, if it has a length of 1, then it turns out the hypotenuse has a length of 2. And that's just the way these ratios work out. So if the shortest side is 1, the hypotenuse has a length of 2. So you can ask yourself, okay, well then what is this third side going to be here? And you could figure that out by doing a little bit of Pythagoras, right? So if I've got this third side, I'll just call it x for now. You could say, well, 2 squared, you could say 2 squared would just equal 1 squared plus x squared. And so this becomes 4 equals 1 plus x squared. And when I move the 1 to the other side, I get x squared equals 3. And then when I take the square root, I get x equals the square root of 3. So this side right here is always going to equal the square root of 3. And so if you have a 30, 60, 90 triangle, your sides are 1 to 2 to root 3, where 1 is the shortest, 2 is the hypotenuse, and then root 3 is your other side. So 1 to 2 to root 3. So if I want to find the sine of 30 degrees, I know that sine is opposite over hypotenuse. That ratio will be opposite 30 is 1, hypotenuse is 2. So the sine of 30 is 1/2. And that's something that you'll be expected to know without using your calculator. For cosine is going to be adjacent over hypotenuse, which means it will be the square root of 3 over 2. Now you can put that in your calculator and you get a big messy rational expression, or irrational number I should say. But That's fine, as is. You can leave it like that. And the tan is just going to be opposite over adjacent, which means it's just going to be 1 over root 3. Now, this is a point where math purists out there will scream and get all upset because I've got a radical on the bottom of that rational expression. We can't leave a radical on the bottom of a rational. We'll get into that later when we talk about radicals. So if you wanted to for now, you could just say, well, I'm just going to multiply this top and bottom by the square root of 3. And then this becomes the square root of 3 over 3. If for now you're not sure how to work with radicals, we're going to learn about them more later. And so that's something that we can explore down the road. So same thing here when we do the sine of 60 degrees. If we imagine 60 degrees, now I'm looking at this angle over here. Opposite over hypotenuse is going to equal root 3 over 2. And for cosine of 60, adjacent over hypotenuse is going to equal 1 over 2. And for the tan, opposite over adjacent is going to equal root 3 over 1, or just root 3. Now there's a certain pattern here, hopefully you're kind of catching on to it, that the sine of 30 and the cos of 60 are the same, and the cos of 30 and the sine of 60 are the same, and so on, okay? Now these, I would not expect you to memorize. It'd be way too challenging to memorize them. But what you should be able to do is sketch out this picture, write out your ratio, 1 to 2 to root 3, and then from that, figure out what those ratios are going to be, okay? Now the other triangle we're going to look at is if it's a 45, 45, 90 triangle. So there's a 90 degrees, and this is 45, and this is therefore then also 45, which means it's both a right angle triangle and an isosceles triangle, which is to say those two sides are going to be equal. So if we, for example, have this side here with a length of 1, then automatically the other side over here will also have a length of 1. And then you could ask yourself, you could do a little Pythagoras and say, okay, well, what is that hypotenuse going to be? Well, the hypotenuse here, maybe I'll call it x, is just going to equal the square root of 1 squared plus 1 squared. Again, just using some Pythagoras. And 1 squared plus 1 squared is 2, so this is going to equal the square root of 2. So if you have a 45, 45, 90 triangle, your ratio of your sides are 1 to 1 to root 2. And what that means is, if we take the sine of 45, that's going to equal opposite over hypotenuse, which is going to equal 1 over root 2. And if, again, bit of a math purist, you're like, I don't want to write the radical on the bottom, you could rewrite that as root 2 over 2. The cosine of 45 is going to be adjacent over hypotenuse, so that's also going to equal 1 over root 2, which again we could rewrite as root 2 over 2. And then the tan of 45, which is opposite over adjacent, is going to equal 1 over 1, which is just 1. Okay? So again, for these triangles, I wouldn't expect you to memorize what those ratios are, but you could just really quickly sketch out a triangle. Think of your ratios, 1 to 1 to root 2 for the 45, or 1 to 2 to root 3 for the 30, 60, 90, and then come up with the ratios kind of on the spot. Okay, that's it for the introduction to trig.